Hello and welcome to this third video of my playlist about carbon dioxide. This video is about carboxylations at carbon by substitution of hydrogen, halides or sulfonates for the preparation of carboxylic acids. Most examples are carboxylations with carbon dioxide, but carbon monoxide is more reactive, and I'll show you also some examples of carbonylations with carbon monoxide. As usual, you can find a PDF version of the slides under the community tab of my channel. Some authors are trying to sell this chemistry as carbon capture to prevent climate change, but this is of course complete nonsense. No synthetic chemistry has ever been run on a sufficiently large scale to have any impact on global carbon emissions. Even the largest synthetic processes, for instance the production of fertilizers or polymers, involve quantities that are only a tiny fraction of the amount of coal, oil and gas we are burning. Let's first have a look at the main mechanisms of carboxylation reactions. Polar organometallic compounds, for instance organolithium or Grignard reagents, are sufficiently nucleophilic to react with carbon dioxide directly. Hydrolysis and acidification of the intermediate carboxylate then yields a carboxylic acid. Polar organometallics can be generated from organic halides or by deprotonation of organic compounds with strong bases. Organolithium compounds and even some Grignard reagents can add to carboxylates and yield ketones. This side reaction may be prevented by adding the polar organometallic to an excess of carbon dioxide or by conducting the carboxylation at a low temperature. Organomagnesium or organozinc reagents are usually less reactive and more selective than organolithium compounds and will yield less ketones. Because the protonation of polar organometallic reagents is much faster than the formation of C-C bonds, the carbon dioxide used for these carboxylations must be carefully dried, for instance by passing it through sulfuric acid and through a cold trap. Dry ice that has been lying around in a Dewar container the whole day is usually no longer dry, but covered by a layer of frozen water and should better not be used for these carboxylations. Another potential side reaction is single electron transfer from the organometallic reagent to carbon dioxide. The resulting radicals might react to the expected carboxylate, but can also dimerize or undergo other unexpected reactions. The carboxylation of organic halides can also succeed with catalytic amounts of palladium or nickel complexes, without the stoichiometric formation of organometallics. The initially formed intermediates do not usually react with carbon dioxide, but require a reduction step to become more nucleophilic. Such a reduction can be achieved with zinc or manganese powder. The initially formed intermediates do however react with carbon monoxide to acyl complexes. These can be hydrolyzed to carboxylic acids, but react also with alcohols or amines to esters or amides. Examples have been reported where carbon monoxide was generated in situ by reduction of carbon dioxide. By the way, it is not usually a good idea to treat polar organometallics, for instance organolithium or organomagnesium compounds, with carbon monoxide. As discussed in the previous video of this playlist, the resulting polar acyl complexes behave like carbines and tend to yield complex product mixtures. Palladium or nickel acyl complexes can also react with one further molecule of carbon monoxide to 1,2-dicarbonyl compounds, which often are trace impurities in the products of such carbonylations. Carboxylation of organometallics with carbon dioxide or carbon monoxide is not always the best method to prepare carboxylic acids from organic halides. Two important alternatives are substitution with cyanide, followed by hydrolysis, and the carbonylation of carbocations. I'll show you some examples in a minute. For carboxylations with carbon dioxide, its solubility in the solvent chosen is of course important. If the solubility is low and stirring is inefficient, polar organometallics will for instance have plenty of time to react with the first carboxylation product to ketones or even tertiary alcohols. A higher pressure is an efficient way to increase the concentration of CO2 in the reaction mixture, but autoclaves are not always available or suitable for reactions with polar organometallics. Here are some solubilities at normal pressure and 25 degrees Celsius for typical solvents that do not react with CO2, like secondary amines. Let's check some specific examples of carboxylations, beginning with alkyl halides and sulfonates. Here, a Grignard reagent was prepared from terzbutyl chloride and then carboxylated with an excess of gaseous carbon dioxide. In these reactions, the difficult part is usually the preparation of the organomagnesium compound, but a number of tricks and improvements have been reported over the years. This here is an example of the carboxylation of an alkyl tosylate with catalytic nickel and a reducing agent, manganese in this case. As in the previous example, the yield was only fair. Here, a benzyl bromide was carboxylated under conditions similar to those of the previous slide. An excess of zinc was the reducing agent and a complete racemization occurred. A similar result was achieved with catalytic palladium on charcoal and carbon monoxide, but in this case no reducing agent was required. As byproducts, a toluene and a benzylic alcohol were obtained. The aromatic bromide remained unchanged. Even allylic alcohols can sometimes be carboxylated directly, without further activation. Here, a nickel catalyst and an excess of manganese brought about the carboxylation with CO2 of an allylic alcohol with complete allylic inversion. The non-allylic hydroxy group did not react under these conditions. In this example, an allylic fluoride was carboxylated once with a copper catalyst and a diboron reagent as reducing agent. To facilitate isolation and purification of the product, the intermediate acid was alkylated at oxygen with hexyl iodide. The combination of a nickel catalyst and manganese also enables the carboxylation of vinyl halides, even chlorides, as shown here. Also, cobalt complexes can catalyze such carboxylations with carbon dioxide. Again, manganese and some ligands were required, the latter to prevent precipitation of metallic cobalt, which would no longer catalyze this reaction. Here, a dilithiated intermediate was generated from a diiodide and an excess of terzbutyl lithium. Treatment with an excess of dry, gaseous carbon dioxide at -30 degrees Celsius yielded a cyclic enone. It is also possible to cleave only one carbon halide bond of a polyhalide with magnesium or lithium. In this example, hexachlorobenzene was converted into pentachlorophenyl magnesium chloride and then carboxylated with CO2. The ethylene bromide was slowly added over the 48 hours reaction time to constantly reactivate the magnesium. In this example, an aryl chloride was carboxylated in high yield with catalytic nickel and a dimeric DMAP derivative as reducing agent. Aryl bromides are more reactive than aryl chlorides and are often preferred as synthetic intermediates. Here, an aryl Grignard reagent was generated from an aryl bromide and then added to an excess of carbon dioxide and THF. A high yield of the expected benzoic acid resulted. One alternative to the preparation of Grignard reagents from metallic magnesium is the transmetallation with isopropyl magnesium chloride, as in this example. Only one of 2 bromine atoms was displaced, and again a high yield of benzoic acid resulted. The more functional groups a starting halide has, the more difficult its selective metallation and carboxylation will become. Here, conversion of the aryl bromide into an organolithium compound required -78 degrees Celsius, and because of the instability of the lithiated intermediate, results of its carboxylation were variable. Better reproducibility could be achieved by conversion into a thermally more stable lithium triaryl magnesiate, followed by an excess of gaseous CO2. The simple Grignard reagent was apparently not tested. The main byproducts were a ketone and the debrominated starting material. Similarly, here tribromobenzene was metallated once with a lithium magnesiate and then carboxylated with Boc anhydride. With an excess of activated metallic copper, a direct one-step carboxylation of aryl bromides can be sometimes achieved, as sketched here. Few successful examples of direct metallations with elemental copper have been reported, and the large amount of copper waste would be a problem. Phenols can be activated in situ with sulfuryl fluoride. In this example, the resulting intermediate could be carboxylated with catalytic nickel and an excess of manganese and carbon dioxide, just like an aryl halide. This example shows that intermediate organolithium compounds are sometimes too reactive, even at low temperature. After treatment with butyllithium and carbon dioxide, only 20% of the expected naphthoic acid was obtained here. The main byproducts were the debrominated starting material and ketones resulting from the addition of organolithium intermediates to the cyano group. A palladium-catalyzed carbonylation with carbon monoxide gave much improved results. This reaction proceeded at 85 degrees Celsius and did not even require anhydrous conditions. Organozinc reagents are quite unreactive, but can be carboxylated under the conditions shown here. Both the zinc-iodine exchange and the carboxylation were slow, though. This is another example of the preparation of a benzoic acid by palladium-catalyzed carbonylation with carbon monoxide. The starting electrophile was a diazonium salt, and no phosphine ligands were required. Carbocations do sometimes also react cleanly with carbon monoxide. In this example, a tertiary carbocation was generated by rearrangement of a secondary carbocation, which in turn resulted from a secondary alcohol by treatment with sulfuric acid. Formic acid was dehydrated to carbon monoxide, and the final acid was obtained in excellent yield. I'll show you now some examples of carboxylation by substitution of hydrogen in the order given here. I've also included some carboxylations of internal alkynes, of silanes and of boranes. The same limitations of polar organometallics I mentioned at the beginning apply, of course, if the organometallic is prepared by deprotonation instead of halogen-metal exchange. Here a carbamate was lithiated enantioselectively and then carboxylated with CO2. Despite the low temperature, the yield of monocarboxylic acid was only low, and a ketone and a malonate were formed as byproducts, because of the high reactivity of the organolithium intermediate. Organosodium reagents are only rarely used, but occasionally these are easy to generate and sufficiently stable and selective to be useful in organic synthesis. Here benzyl sodium was prepared from toluene and then carboxylated with carbon dioxide. By keeping the carboxylation temperature low, phenylacetic acid could be prepared with high selectivity, but at a higher temperature the main product became phenylmalonic acid. At this higher temperature, deprotonation of sodium phenylacetate by benzyl sodium apparently became faster than the rate of carbon dioxide diffusion into the reaction mixture. At 180 degrees Celsius, however, in this example no malonic acid but only an aryl acetic acid resulted. Malonic acids decarboxylate readily, what might have been the reason for the improved selectivity. 1,3-dithioanes are acidic and can be deprotonated by various bases. Here, heating potassium triphenylacetate in DMF to 60 degrees Celsius led to decarboxylation and the formation of trityl potassium. The latter deprotonated the dithiane, which then reacted with the carbon dioxide formed by decarboxylation. This is an example of allylic deprotonation and carboxylation with the aid of ethyl aluminum dichloride and dibromopyridine. Interestingly, no isomerization to the acrylate occurred. In this example of allylic carboxylation, the initially formed acid added intramolecularly to an alkyne. Again, no particularly strong base was required, just a mixture of DBU and silver benzoate. Here, deprotonation of the allylic position yielded a vinylogous ester enolate. Treatment with carbon dioxide then gave a cyclic anhydride by displacement of a phenolate. Halogenated arenes are quite acidic and can sometimes be metallated even with weak bases. In this example, a 1,3-difluorophenyl group was lithiated with butyllithium and then carboxylated at low temperature. Metallated haloarenes are dangerous intermediates that may decompose violently when allowed to warm up. In this instance, the intermediate dimerized at temperatures above -60 degrees Celsius. Here 1-bromo-3-chlorobenzene was lithiated and then carboxylated with carbon dioxide in excellent yield. In this case, LDA had to be used as base because butyllithium would have caused a bromine-lithium exchange. If the lithiated arene was allowed to warm up above -70 degrees Celsius, however, an exothermic decomposition occurred. Most products were probably formed from intermediate arenes. Benzothiophene can be metallated at position 2 with tertiary alkoxides. As in one of the previous examples, a special reagent provided both carbon dioxide and the required base. The same conditions also brought about a clean single carboxylation of 1,3,5-trichlorobenzene. Unlike benzothiophene, indole is carboxylated at position 3, as shown here. Carboxylation at nitrogen probably also occurred, but carbamic acids are thermally unstable and usually decarboxylate during workup. Here, a 2-methylbenzothiophene was carboxylated twice and in high yield by treatment with carbon dioxide and an excess of lithium terz butoxide and cesium fluoride at 150 degrees Celsius. The carboxylation of phenol to salicylic acid is of great commercial relevance, but other phenols can also be carboxylated. The products are, however, phenylogous carbonic acids and readily decarboxylate upon heating. In this example, resorcinol was carboxylated with aqueous bicarbonate as base. Mostly one regioisomer resulted. Few examples have been reported of acid-catalyzed carboxylations with carbon dioxide. Here, benzene was converted into a mixture of benzoic acid and benzophenone by heating with CO2 and aluminum chloride. One problem is that benzoic acid and the water resulting from ketone formation both deactivate aluminum chloride. Similarly, toluene could be carboxylated with a mixture of aluminum bromide and trimethylchlorosilane. No ketone was formed in this case, only a mixture of two isomeric toluic acids. Propiolic acids can be prepared from terminal alkynes and carbon dioxide. In this example, the iron catalyst was required to accelerate the formation of sodium amide from ammonia and sodium. Carboxylation then gave a fair yield of the expected acid. With weaker bases, for instance alkali carbonates, no complete deprotonation of alkynes can be attained, and carboxylation will require copper catalysis or higher reaction temperatures, as in this example. Here, the carboxylation was conducted in DMF under pressure at 120 degrees Celsius. No carboxylation of the phenol occurred. In this example, the carboxylation of a terminal alkyne succeeded at room temperature, but 5% of copper chloride was also required. Copper salts react with terminal alkynes to copper acetylides, which are more nucleophilic than non-metallated alkynes. Unfortunately, these copper acetylides readily yield diacetylenes, and it is important to remove all traces of oxygen or other oxidants from the reaction mixture. Copper acetylides also tend to precipitate and to explode, and I would rather avoid copper catalysis if possible. Silver acetylides are similarly explosive. Nickel complexes sometimes catalyze the carboxylation of internal alkynes, both with carbon dioxide or carbon monoxide. Here, carbon monoxide was generated from formic acid and catalytic pivalic anhydride. Interestingly, internal carboxylation was the preferred pathway, and no terminal carboxylation occurred. Here, an internal alkyne was first metallated stoichiometrically with an aluminum hydride and then carboxylated with carbon dioxide in the presence of copper chloride and potassium terz butoxide. A high yield of the expected lactone was obtained. Also in this example, an internal alkyne was first metallated quantitatively by reaction with an excess of phenylmagnesium bromide. Additions of polar organometallics to alkynes or olefins can be catalyzed with late transition metals, for instance nickel, palladium or copper, because the corresponding organometallics are more polarizable than organolithium or magnesium compounds and have a higher tendency to add to CC double bonds than to carbonyl groups. In this instance, the intermediate Grignard reagent was then carboxylated at room temperature. Here, the addition of butyl magnesium chloride, first to an internal alkyne and then to an alene, was mediated by an excess of copper chloride. Again, carboxylation with CO2 was fast and yielded mostly the expected lactone. In this example, an internal alkyne was first converted into a vinylic organozinc intermediate by treatment with an excess of dimethyl zinc and a nickel catalyst. Carboxylation yielded a mixture of two isomeric acrylates. Here, a diene was cyclized by treatment with catalytic nickel and an excess of diethyl zinc. Again, a vinylic organozinc intermediate was formed that reacted with carbon dioxide to the corresponding carboxylic acid. Here, however, no addition of an ethyl group to the alkyne occurred. Internal alkynes can be transformed into substituted maleic acid anhydrides. This reaction is assumed to proceed by twofold insertion of CO2 into the nickel-carbon bonds of an intermediate nickel-alkyne complex. Ketones are slightly more acidic than terminal alkynes, and ketone enolates therefore less nucleophilic than deprotonated alkynes. Under optimized conditions, it is however still possible to carboxylate ketone enolates with carbon dioxide. The resulting beta-ketocarboxylic acids are thermally unstable and should better be esterified to prevent decarboxylation. In this example, acetophenone was carboxylated at ambient pressure with a mixture of triethylamine and magnesium chloride as Lewis acid. Also, zinc phenolates can bring about the carboxylation of acetophenone. Polar aprotic solvents like acetonitrile or DMSO seem to be particularly well suited for this reaction. In this example, cyclohexanone was carboxylated twice with magnesium methoxide as base, and the intermediate diacid was esterified at room temperature with methanol. Esterified 3-keto esters are thermally much more stable than keto acids. Diazoketones are similarly acidic as simple ketones and can be deprotonated and alkylated or acylated with various electrophiles. Interestingly, in this example, reaction of a diazoenolate with carbon dioxide was faster than direct benzylation with benzyl bromide. Thus, both electrophiles together did not yield a mixture of products, but mainly a benzyl diazoester. Like ketones, also hydrazones can be carboxylated. In this example, a pyrazolone was prepared by heating a hydrazone of pinacolone with an excess of lithium terzbutoxide under an atmosphere of CO2. Under similar conditions, tosyl hydrazones do not yield pyrazolones, but undergo ipsocarboxylation to yield acrylates instead. Again, like in the previous examples, no stoichiometric metallation with strong bases was required. I'll show you now some examples of the carboxylation of olefins with carbon dioxide. Hydroformylation with carbon monoxide followed by oxidation to the acid will often be a superior strategy, but on occasions the CO2 route may offer advantages. When enones are treated with magnesium and trimethylchlorosilane, like in a pinacol coupling, homoenolates are formed. Here, such a magnesium homoenolate was carboxylated with carbon dioxide, and after hydrolysis, a gamma-keto acid resulted in high yield. In this example, a metallated nitrile was generated from a substituted acrylonitrile, diethyl zinc, and catalytic cobalt. Carboxylation gave a high yield of the cyanoacetic acid. These are thermally more stable than acetoacetic acids, but may still decarboxylate when heated. Even ethylene can be converted into acrylic acid with carbon dioxide. Here, this interesting reaction was accomplished with a palladium diphosphine complex and sodium isopropoxide, but the turnover was not yet sufficient to compete with the oxidation of propene. This carboxylation was assumed to proceed by insertion of CO2 into one palladium-carbon bond of a palladium-ethylene complex, like in the nickel-catalyzed carboxylation of internal alkynes discussed above. Boranes and boronic acid derivatives can be carboxylated directly with the aid of some catalysts. Here, a mixture of catalytic copper and potassium terzbutoxide was used to bring about such a carboxylation with CO2. In this example, a boronic ester was generated directly from an allylic alcohol and then carboxylated again with catalytic copper and potassium terzbutoxide. Complete allylic inversion occurred in each step. Treatment of silanes with fluoride yields carbanions or intermediates strongly nucleophilic at carbon. Here, an enantiomerically enriched alpha-aminosilane was carboxylated by treatment with carbon dioxide and cesium fluoride at low temperature, with only partial racemization. In this example, an amine quaternization, ylide formation, carboxylation, and Stevens rearrangement were carried out all at once. A high yield of an amino acid ester resulted, despite the many potential side reactions. On this and the next slide there are some further examples which you can also find in the description of this video. A copy of the slides in PDF format is under the Community tab of my channel. The next video of this playlist is about carboxylations with carbon dioxide, add nitrogen and oxygen for preparing carbamates, organic carbonates and ureas. See you there.